Now we will discuss simple stress. Stress in composite bar. In previous lecture, we have discussed about the stresses in a simple beam. Now we will discuss the composite bars. A composite bar may be defined as a bar made up of two or more different materials joined together in such a manner that the system extends or contracts as one unit equally when subjected to tension or compression. The extension or contraction of the bar, here we can see there are two different bar of different elements 1 and 2, and these are applying a equal force of P and the same length of L. P1 is the load carried by bar 1, and suppose A1 is the cross sectional area of bar 1. Sigma 1 is the stress produced in the bar 1 and E1 is the Young's modulus of the bar 1. P2, A2, sigma 2, E2 corresponding values of bar 2. Let P is the total load on the composite bar, L is the length of the composite bar, and del L is the elongation of the composite bar. Then we know that the total force is the sum of the load P1 and P2, and sigma 1 is the P1 upon A1, stress is in bar 1, and stress in bar 2, and the strain in bar 1 epsilon equal sigma 1 upon E1 equal P1 upon A1 E1. Elongation in bar 1 is del L1 equal P1L upon A1 E1. Elongation in bar 2 is del 2 equal to P2L upon A2 E2. Therefore, these formulas we have discussed in the previous lecture. The elongation in the bar. Now, therefore, the change in the length or the elongation of both the bar will be same. Del L1 will be equal to del L2. The change in length of both the bar will be equal. Therefore, P1L upon A1 E1 equal P2L upon A2 E2. This implies that sigma 1 upon E1 equal sigma 2 upon E2. But we know that the total force is the sum of the two forces P1 and P2. Therefore, sigma 1 A1 plus sigma 2 A2 is equal to P. The ratio E1 by E2 is known as modular ratio of the two materials. P equal P1 plus P2. Therefore, sigma 1 equal P1 upon A1, epsilon equal to sigma 1 upon E1, and P1 upon A1 E1. Del L1 is equal to P1L upon A1 E1, del L2 equal to P2L upon A2 E2. These formulas will apply for calculation of the composite bar problems. Del L1 equal to del L2, therefore P1L by A1 E1 equal to P2L by A2 A2. Sigma 1 upon E1 equal to sigma 2 upon E2, P equal to P1 plus P2, sigma 1 A1 plus sigma 2 A2, and therefore P1 equal to P into A1 E1 by A1 E1 plus A2 E2. Bar with cross-sectional varying in steps. A typical bar with cross-sectional varying in step and subjected to an axial load length of three portions L1, L2 and L3, and the respective cross-sectional areas are A1, A2, A3. E is the Young's modulus of the material, P is the applied force. In figure you can see there is a tensile force P acting on a varying cross-sectional area bar varying in steps. Forces acting on the cross section of the three portion, it is obvious that no maintain equilibrium. The load acting on each portion is P only. Now we will draw the free body diagram of each section. Section through 1, 2 and section through 3. We will discuss the stresses and the strain and the change in length of each section individually. In portion 1, stress will induce sigma 1 P upon A1. For portion 2, sigma 2 equal to P by A2, and for third portion, stress will be equal to force upon area of the third part. For strain in section 1 will be equal to sigma 1 by E, for portion 2 sigma 2 upon E, and for portion 3 this will be equal to sigma 3 by E. Similarly, the extension will be equal to, for portion 1 will be PL1 by A1E, for portion 2 PL2 by A2E, and for portion 3 PL3 by A3. The total elongation will be del 1 plus del 2 plus del 3. Here we can take P and E common, and the final formula will be P upon E under bracket L1 by A1 plus L2 by A2 plus L3 by A3. Now we will discuss thermal stress. Stress due to change in temperature. Whenever there is some increase or decrease in the temperature of the body, it causes the body to expand or contract. If the body is allowed to expand or contract freely with the rise or fall of the temperature, no stress are induced in the body. But if the deformation of the body is prevented, some stresses are induced in the body. Such stress is known as the thermal stresses. Let L is the original length of the body, T is the rise or fall of the temperature, and alpha is the coefficient of thermal expansion. Therefore, increase or decrease in the length will be equal to del L will be equal to L into alpha into T. If the ends of the body are fixed to resist support so that its expansion is prevented, then compressive strain induced in the body. Then compressive strain will be equal to del L by L is equal to L alpha T upon L will be equal to alpha T. Therefore, thermal stress will be equal to epsilon into E or alpha TE. If the free expansion is prevented fully, since support is not permitting the support force P developed to keep it at the original position, magnitude of this force is such that contraction is equal to the free expansion. Del L is equal to alpha L. PL upon A will be equal to alpha TL. If free expansion is prevented partially, expansion prevented del L is equal to alpha TL minus del. PL upon A equal to alpha TL minus del. Linear and lateral strain. Consider a circular bar of diameter D and the length L subjected to a tensile force P. Due to tensile force, the length of the bar increases by an amount del L and the diameter decreases by an amount del D. Similarly, if the bar is subjected to a compressive force, every direct stress is accompanied by a strain. It is in its own direction is known as linear strain, and an opposite kind of strain in every direction at right angles to it is known as lateral strain. When a body is stretched within elastic limits, the lateral strain bears a constant ratio to the linear strain. Lateral strain upon linear strain equal to constant. This constant is known as Poisson ratio and is denoted by 1 by m or mu. When a body is subjected to a system of forces, it undergoes some changes in its dimension. The volume of the body is changed. The ratio of the change in the volume to the original volume is known as the volumetric strain. Volumetric strain will be equal to change in volume upon original volume. Volumetric strain of a rectangular body subjected to an axial force is given by del V upon V equal epsilon 1 minus 2 upon m.